Hello, 8th grade. We're going to continue on with our last part of radioactivity, and that is the emission of a gamma ray. And that's what we call, just fix this a little bit, that's what we would call the gamma decay, okay? So there's alpha decay, there's beta decay, and there's gamma decay. And we talked about how in alpha and beta, something is being emitted from the nucleus, okay? And usually that will result in some form of transmutation, right? The element is going to change over into something different. In the case of gamma decay, it does result in the release of something from the nucleus. However, it does not result in transmutation, okay? And we're going to talk about the scenarios and what exactly is happening. So, gamma decay when gamma decay occurs, what's happening, what's being released is energy. So the nucleus releases energy in the form of a photon. Not a proton, don't get it confused, not a proton, a photon. So what's going to happen is the nucleus is going to release is going to undergo gamma decay. And the nucleus is going to release what's called just a form of energy, which we know is a photon. And you guys are familiar with photons because you know about this from many of the other things that we've talked about, right? Photosynthesis, we discussed this last year. I think we discussed it even this year. So we're familiar with photons, and we're going to talk a little bit more about what exactly a photon is and the different portions of the photon. But one of the things that you need to understand is that in the case of gamma radiation, it's not going to be the release of any type of subatomic particles like the other types of decay, but just in the case of releasing energy. That's it, okay? So there are two scenarios where gamma decay will occur. Okay, there are two times where this will happen, okay? You know what, let's just write down, before we get into two scenarios, I want to talk a little bit more about gamma radioactivity. This photon over here is a very high energy. Energy, yes. It's a very high energy wave. It has various different parts to it. We know we'll talk about the wave properties about it in a second, but it has a very, very high energy. And we know that this is produced by the sun. By the way, the sun also goes through a form of a nuclear change, but in that case, there's not what we would call, in this case, the cases that we're learning, we would call nuclear fission. Fission, which means to split. And the reason why it's called fission, right, in the case where it's splitting, is because things are being sent out of the nucleus and things are being separated from what the nucleus was, that hole that was. Now it's going to release different particles, and that's called nuclear fission. Okay, and that changes the nucleus, right? It changes the number of protons in the nucleus, right? In the case of on the sun, for instance, that's called nuclear fusion. And fusion is when things merge, right? When they merge together, they fuse together, okay? In the case of the sun, right, and photons being released by the sun, right? We talk about photons in the sun all the time, right? Because what's happening is that there's actually nuclear fusion, where two hydrogens are going to come together to form a helium, right? So you're going to have a hydrogen with one proton, another hydrogen with another proton, and they're going to come together and they're going to fuse together, and that's going to form helium, okay? These are two different types of radioactive nuclear radioactivity would be either nuclear fission or nuclear fusion. What we've been discussing till this point has always been nuclear fission, including gamma radiation. What's going to end up happening is there's going to be a very high energy wave known as a photon that is going to be released. Okay, so we talk about this high energy wave. We understand that it doesn't matter what kind of nuclear reaction is occurring, either fission or fusion, it has the potential to release this proton. And that's why the sun, photon, and that's why the sun does release photons continuously, because it's constantly going through nuclear fusion. All right, this is a high energy, right, that's going to be released in the case of gamma. We'll talk a little bit more about that and why that happens. And we know that the nucleus does not undergo transmutation, okay? And we'll talk about why and how we can actually calculate that. So there are two scenarios that will basically result in the release of a gamma ray. So two scenarios. My black marker is not working so well. All right, so in the first case, when an alpha or beta decay occur, remember, an alpha or beta decay, when that happens, it's releasing particles from the nucleus, okay? So when that happens, it will also release a gamma ray, or will also release a gamma radiation. Let's just say radiation, okay? So it can happen in conjunction with an alpha or beta decay. So either of those scenarios will release whatever, let's say it's an alpha decay, it will release a helium, and also gamma will be released as well. That energy is going to be released as well. Again, remember, in the case of alpha or beta, we're having like shifting in the nucleus, right? The nucleus is now going to start to change. And so things kind of get shifted around. And when that happens, right, the energy within that nucleus can start to change too. And then the nucleus is going to send out that energy in the form of gamma radiation, right? The second scenario is the nucleus, when the nucleus is in an excited state, it releases gamma to decrease the energy level in the nucleus. So there are two scenarios. One is when alpha or beta decay are occurring, and when they are occurring, the gamma decay is going to happen simultaneously. Or when the nucleus is in an excited state. For whatever reason, the nucleus can become in an excited state, and when that happens, now there's too much energy within that nucleus, and so that nucleus is going to release that energy in the form of gamma radiation. And when that happens, that nucleus is going to re-stabilize, okay? And this will re-stabilize the nucleus. Okay, so in those two scenarios, we're going to end up in a situation where gamma radiation is going to be released. And let me get another paper to continue on, because this one had a lot of notes on it. So to kind of finish off this concept of gamma, just Can we put it here? Yeah, I guess we can put it here so that we can have both of these up at the same time. That would be great. So in the case of gamma, we know that it's energy, right? And energy doesn't have a charge in this case, right? There's no charge. There's no mass, okay? It's an energy form. And so I'm going to show you how we're going to write gamma. But hopefully you guys understand the different scenarios of why a gamma radiation will occur. So gamma is actually written like this, okay? I don't know if you guys can see. Let's try to move the camera a little bit. Okay, so it's written like this. It's kind of like the Hebrew letter ayin, and it has 0 charge and it has 0 mass. So if I'm looking at a gamma particle, this is what the symbol is that I would be looking at. Beta would be either -1 and 0 or a +1 and 0. And an alpha would be a helium, and that would be whatever, 2. It's not +2, it's just 2 and a 4. By the way, some would write alpha. Alpha looks like this, with a 4 and a 2. Would write an alpha particle like that. But right now we're just focusing on the gamma particle and what that would look like. So if I were to write out an equation showing the gamma radiation, let's talk about the different scenarios, okay? So let's start with scenario number 2. So scenario number 2, the atom is in an excited state and it's going to release energy to stabilize, to get down from this excited state, okay? And so what's going to happen in this scenario is, let's say I have iodine. How would I represent iodine being in an excited state? The way I would represent it is I would put like a little star, an asterisk right over there, to show that the iodine is in an excited state. Okay, this is all I need to represent. Now, of course, I have to put in the amount of protons and the atomic weight. So the amount of protons iodine has is 53, and let's say the atomic mass is 125. So this is what the iodine would look like when it starts off in an excited state. Hopefully you guys can see me. Okay, now I would show an arrow showing what's going to be produced. So we know that it's going to release a gamma. So we have this gamma symbol. And then there's going to be something else. But we know that in the case of gamma, it's not going to undergo transmutation. Okay? And so what's going to happen in this case is I have our gamma. And I will show the iodine with it as its atomic symbol. So the I. I will show the 53 because iodine has 53 protons, and the atomic mass doesn't change either, so it would be 125, okay? So if you notice here, nothing changed at all. It's the exact same element. The only difference is it's no longer in an excited state. So when the atom is showing that it's in an excited state, right, in this case, once it releases this gamma, it's no longer in an excited state. It's back to being stabilized, okay? And so this would be scenario number 2. Let's write the equation for scenario number 1. Let's go to purple, okay? So in scenario number 1, it's when I have either alpha or beta decay occurring, it will occur simultaneously with the alpha or beta decay. So scenario number 1. So let's write an example. So if I have, let's say, cobalt, okay, which is CO. By the way, this would look like it's carbon monoxide because it's C and a capital O. I should have made a lowercase o, indicating that that's cobalt. And that would be atomic mass numbers. Number 27. Atomic mass, let's say, is number 60. Let me rewrite this because it looks a little bit messy. So cobalt, number 27 and 60. Okay, and it's going to undergo beta electron decay. So -1, okay, and there's a 0 mass. Now, by the way, in the case of a beta electron decay, we are gaining a proton, right? So if we're gaining a proton, what's going to happen is that my atomic number is going to go up to 28, right? That's my transmutation. It's changing to number 28. The mass doesn't change, so I'm still going to have 60. And if I look at my periodic table, the element that is number 28 is going to be Ni, which is nickel. Okay? So this looks like a typical, I keep hiding behind the wall. This looks like a typical beta electron type of equation, right? So where does gamma come in? Well, if I also, in this scenario, if there was also a gamma decay, I would also have the gamma symbol. And it changes nothing as far as my conservation of mass, changes nothing as far as my conservation of atomic number, right? Because if I had my 28 minus 1, I would end up with 27. If I had my 60 plus 0, I would still be at 60. These two zeros obviously contribute nothing as far as the atomic mass or the atomic number. And so it's just basically an add-on. Now, not every time does that an atom goes through beta or alpha decay is it going to also go through gamma decay, but very, very, very likely, okay? And so a lot of times in these equations, we're going to end up seeing this decay. So two scenarios. We have the gamma decay where the element is in an excited state. And we have the gamma decay when the element is undergoing either an alpha or a beta decay. All right, we're going to stop here. We're going to continue on tomorrow, showing exactly what a gamma wave looks like and how that can be effective or harmful, and where their energy levels are coming from. So we'll stop here today. Have a wonderful day, and we'll see you later.